Yeah, hi everyone. Today we have Yuncong as our speaker. He's a graduating PhD from Berkeley, and I think he's joining Shanghai Jiaotong University this fall. Yeah, let's welcome him.
Yeah, also nice to meet you, and thanks for your kind introduction. So today I'm gonna introduce our work Gemini, which is an elastic proof system for diverse environment. So it's many concerned problem about how to make make the zero-knowledge proof system to support very large instance, and also how to do it in practice. This is a joint talk with Jonathan, Alessandro, and McKelly, and also we presented in this year's Eurocrypt. I think it's just several weeks ago. And feel free to interrupt me if you have any question during my talk, and I can answer your question. Okay, so let's get started. So I just heard of your introduction, self-introduction, and it seems that some of you guys already know a lot about, work on the area of the zero-knowledge proof, but I don't know about others. So how many of you have know something about zero-knowledge proof and the Succinct argument? You can raise your hand. Okay, I think many of you, have the knowledge. So maybe I just give a quick reminder. So the succinct argument system or the proof system allows the prover to prove to the verifier such that to show that it knows that secret witness, and to show that this witness will satisfy a particular relation. And depending on what kind of proof system it's using, it can be either interactive or non-interactive, or either multi-round or just single round. And importantly, we are interested in the succinct argument. So by succinctness, we mean that the message the prover sent to the verifier should be very short, very succinct. So sometimes it's logarithmic to the size of the statement size, or sometimes it's a constant. And also the verifier time should be the verification should be also be very efficient, like it shouldn't no longer than the statement size. And this is very useful in reality because for example, in the blockchain system, we don't want to spend a lot of storage resources to store the zero-knowledge proof. So we want the succinct argument. More importantly is that we're also interested in the pre-processing succinct arguments, which means that before the prover and the verifier interact with each other, there may be a pre-processing step that will take the statement as an input and output some public string or public parameter, and this will help accelerate the verification process. So if there's no pre-processing step, then the verifier at least need to read the whole statement or the whole circuit into the memory. So the verification cost is at least linear to the size of the statement. But with the pre-processing, because it can take the public string or a public input as a public parameter as input instead of the statement itself, so the verification can be very fast, like logarithmic or constant time. So also that's the reason why we are interested in the pre-processing succinct arguments, because for example, in the blockchain setting, there might be many verifiers. For example, each miner may be a verifier. Then we want the verification to be very fast because we don't want it. The whole network delay should not be will be affected by this verification cost. Okay. So this is the literature, and actually during there are a line of work studied the succinct argument and zero-knowledge proof, and actually we already have some very nice results. So for example, we know how to do the proving very fast. We know how to do the linear time prover. Also, we know how to make the verification very fast, like constant verifier or logarithmic verifier. And also we know how to make the proof very short and how to remove the setup. But this is still not the end of the story. And it turns out that the proving space becomes a problem right now. But the thing is that sometimes when you run the prover program, it may prove satisfiability of a circuit with billions of gates. You cannot even run this program because the circuit size itself is already outside the budget of the outside the memory budget. So the program will just crash automatically because there's no enough memory. And it turns out that this, becomes a critical problem right now because of the development of blockchain. So previously, when we want to prove a SHA-256 compression hash function, it may already take 30,000 constraints. And if we use it in some early application like Mocha tree or Zcash and so on, it may already need 100 times more constraints, and it's already outside the benchmark result of some paper. And then more recently, people are interested in larger and larger application, and also the data on the blockchain becomes larger and larger. So for example, for the ZK rollup, it may involve billions of transactions or millions of transactions. Then the number of constraints may be even 1,000 times more, or several thousand times more constraints. And actually, even in the modern implementation, like industry, like the SNARK system, the industry using like Marlin Planck implementation, it cannot even support such a big size, and it really turns out to be a problem. So to solve this problem, people are interested in the space efficient argument. And also this is a long line for work. And in the early stage, people make use of the recursive proof to maintain the time and the space efficient. So what they are doing is that, for example, given a big circuit, you can just split it into several different small circuits, and you prove the satisfiability of each small circuit, and you use a recursive proof to aggregate all the proof together, or you do an incremental verification. So you just prove little by little. But this is symbiotically is good because you preserve the time and the space complexity. But in practice, the concrete efficiency will be affected a lot. So first, to do the recursive proof, you must encode the verifier algorithm into the constraint, which already incurs a large overhead. And the second, in order to do recursive proof, you have very limited choice of the curve and the groove you are working on, or field you are working on. It usually will have a large security parameter. So even a single operation may incur a large overhead. And moreover, sometimes you need to support some kind of non-native operation, which will also make a recursive proof much worse in practice. So recently, people proposed some kind of streaming algorithm to support the space efficient argument. And I think one of the author is in our channel, the Pratik Soni. Yeah, he is one of the author of the prior paper. They propose space efficient argument based on the group of unknown order, and I think it's BHRS 20 and 21. So that's how we recently view this problem. So what does it mean by have a streaming prover? So in practice, how we model it, it can be like that. The prover will not take the whole input into the memory and have a random access, a memory access over it. Instead, the input will just be like a input string to the prover. So the prover will download the element of the input little by little, element by element, and load it into the memory, and use this string to produce this proof. And in practice, you can view it as like a network string. For example, a network string from the cloud server. So for example, you have a mobile phone which have a limited memory. You just download the string from the web server. Or you can view it as a file string from the disk. So for example, if you are using a specialized hardware like FPGA or ASIC, or you are using CPU or GPU, but the memory is limited, and the input file is stored on your disk, and you just input, you just take the file string as input and output and generate the proof. And this is how we view it in practice. And in theory, we can view it as a Turing machine, which has the oracle access to the input string. So it will not have a random access to the location of the input. Instead, it will have the streaming access. It can either start from the beginning or ask for the next element of the input. So have the streaming oracle access and output the proof. So this is how we model the streaming prover. And on top of that, in our paper, we also propose the notion of elasticity. So it's kind of means that you have a single proving protocol, but it have two different realization. There's one in the time efficient realization, which is means that you have enough memory and you optimize for the time performance. The second is that you have limited memory or limited space, so it's optimized for space, and it will still allows you to generate proof. And the important thing is that they follow the same protocol description. So the output of these two realization is identical, so it's output the same proof. So from the verifier point of view, it does not care what kind of realization you are using on the prover side. It can either be time efficient or space efficient, but the proof is the same, and the verifier just receive it and verify it. And as I said, with in the preprocessing succinct argument, the verifier can be very fast, the logarithmic or constant. So even if the statement size is very, very large, the verifier can just verify the proof very fast without the concern of the space. So this is our main theorem. So we prove that there exists an elastic preprocessing succinct argument for circuit sensibility, and it admits two realization for the prover. So there will exist a time efficient prover that's run in linear time, either in linear time in linear space, or there exists a space efficient prover runs in quasilinear time and the log space. And as I said, the proof is independent from the prover instantiation. So the verification cost is always runs in logarithmic time. So it does not care about what kind of realization you are using. And how to compare this with prior work, like the practice prior work. So one thing is that so I think the symptotic cost is almost the same when comparing these two work, but we have some kind of concrete efficiency and a concrete instantiation, and also we have a concrete implementation and a benchmark. And I think we have a good, better concrete efficiency. And the second, when the circuit size has some special, property or have some special form, like it's an inner product circuit or it's a sum check circuit, our space efficient prover, time can even be reduced. Instead of n log square n time, it can be run in n log n time. And I think this is important. Okay, so this is an overview of the background and our work. Any problem so far?
So you said you have a concrete implementation, so I guess the constants, the hidden constants are not too bad.
Sorry?
I'm just asking how big are the hidden constants?
Yeah, I think the constant is that so the prior work used the groups of the unknown order. I think that we still do not know that if there is a efficient, realization for it, and they do not have the concrete, the implementation or the protocol detail. So it's hard to measure their concrete performance. I think that's the thing. I think the prior work is more about in theory, they show that it's possible to construct a symptotically efficient protocol if you have the group of unknown order assumption.
Okay, thanks.
But for our case, we just use some very realistic assumption, like we use a bilinear map and the pairing and the group operation. And all these things are already used in the prior practical proof system, like Planck or Marlin. We basically use the same assumption and the same in the same, backend crypto operation. So so our system is ready for the practice use, I think.
Yeah, I had a couple of questions. So can you say a little bit about what kind of setup do you guys need? Is it a transparent setup or a trusted setup?
Yeah, so we are considering the universal setup. So it's the same assumption used in the Martin and Planck. And the reason is mainly because we are using the KZG polynomial commitment, which requires the universal setup. But in principle, you can replace it, but you also need to rethink about how to make it work in the space efficient way.
And another question was, so you have this two different modes of proving, one gives you a better time, the other one gives you better space. And I was wondering, like, this protocol will be an interactive protocol. So can you actually switch between the two modes?
Yeah. A good question. Actually, that's the thing I forgot to say. Yeah, we support the switching. So there's a cool thing with our elasticity is that because they follow the same protocol, so it's really possible. And actually, we implement it. So in the middle of the proving, you can switch from the space efficient to the time efficient if you found that the rest of the computation is within the memory budget, so or within the threshold of the memory budget, then you can switch from the space efficient to the time efficient, and you can get optimized performance for the rest of the proving. So that's one of the benefits of our elasticity. Thanks for the question, because I forgot to say that.
Thanks so much.
I also had a quick question. Are you streaming the proofs to the verifier, or are you just building it up on the prover's end and then sending it over at one shot?
So the input to the prover is in a streaming way, but the input to the verifier is actually, in the normal form. So as I said, the verification cost is just log n, which means that the input to the verifier is also log n.
Okay.
That's the power of the preprocessing. But on the other hand, it also means that our preprocessing step requires a streaming algorithm. But it's the preprocessing computation is also repeated in the prover, so it's not a problem. So the preprocessing will take the circuit or the instance as the streaming input and output some very short string, like very short commitment. And the verifier only needs this commitment as the input, and can run the verification on top of this commitment, and also the proof sent from the prover. And the overall verification cost is just log n. So the overall space cost of the verifier is also log n. So the verifier, so in short, the verifier does not need the streaming input, because its input is also already very short. Any other question? Okay, I guess I can continue. So our proof system work with the R1CS, R1CS system, and I think many of you have heard of it. So any circuit's satisfiability problem can be transformed to this R1CS system. So for example, if you give me a circuit, I can just translate it into a equation like I have three metrics A, B, and C, and also there will be if the circuit is satisfiable, then we can show that there must exist a vector Z such that the equation here will be satisfied, and the circle here means Hadamard product. So when you use the matrix A times Z and B times Z, we will show that AZ times BZ will equal to CZ. So any circuit satisfiability can be transformed can be translated to this form. And how to do that is also very easy. You just look at each gate in the circuit and just put the 1, 1, 0 into the matrix. And this will stand for computation of one gate in the circuit. And this is already commonly used in the prior proof systems like Martin and others. Yeah. So normally in the normal proof system like Martin, it will just take the R1CS matrix and ABC and Z as input and process on top of it. But if the prover's memory is very limited, then this is impossible because the matrix size itself will already, outside the memory budget. So the prover need to take the stream of the R1CS relation as the input. So it consists of, first, it will consist of a full instance, like for the vector Z, it must have a streaming access of the element of Z one by one. And also for each matrix A, B, C, it will also have the streaming access to all the non-zero entry in each of these metrics. And it can be either be row major order, like the non-zero entry in the first row, in the second row, in the third row, or in the column major in the first row, first column, second column, and third column. It really depends on what kind of proof system and what kind of order the proof system prefer. And the third, we require the computation trace. So we require the streaming access of the result of A times that and a stream access to the, and also for the B times that and C times that. This can be viewed as a computation trace for the circuit. So when you evaluate the circuit, you must have some intermediate result for the gate output, and this is a computation trace. And we ask the prover to have the streaming access to this computation trace. And if the circuit have some special form, like it's an inner product or sum check, then this computation trace can just be simply generated by composing the stream of the matrix string, like the stream of matrix A and the stream access of the Z vector. You can just compose these two streams to compose the computation trace. But otherwise, then we need the streaming access to this computation trace. So this is how we model the input to the prover. And now I'm gonna introduce our idealized protocol or our information theoretical protocol. The core of this protocol is elastic polynomial IOP, interactive oracle proof, for the inner product argument. So the inner product argument is actually widely used in the area. It's used to prove that given you two vector, you prove the inner product of these two vector is equal to some claimed result. And the reason we the way we usually do it in the prior protocol or in most inner product argument is that we will reduce this problem to a sub-problem with smaller size. For example, we reduce the two vector, with size n to a sub-problem, each f prime and g prime, and each of these vector will only have size n over 2. And we will repeat this reduction, and finally you will just get two constant size vector, and the verifier can just verify it very easily. And this is usually how we do it. So we usually will fold these vectors, or you can either do an even and odd fold, or you can do the left and right fold. They are essentially, there's no much big difference. And at each round, the verifier will send some randomness, like R1, R2, Rn, and the prover will reply with some intermediate results. And then after log time, as you can see, after the log time of this folding, because each time the size of the vector will divide by 2. So finally, when you have a two element, Fn and Gn, these two vectors just have a single element. So the verifier can just do a single multiplication to check whether the result is correct. And because of the reduction, if this final sub-problem is satisfied, then the original problem is also satisfied. And moreover, depends on the way we do the folding. Like if we do the even and odd folding, following the paradigm of the FFT, we will see that each folding result can be viewed as a linear combination of the randomness sent by the verifier. Like this F prime prime can be viewed as a random combination of R1 and R2. So finally, we will see that the final result Fn and Gn are actually a multivariate polynomial evaluation. And so the verifier can just query the multivariate polynomial to check whether the Fn and Gn satisfy the argument. Okay, so it's very easy to see how to do this inner product in linear time, because each time we will divide the vector size by 2. So in the first round, the prover will process a vector with size n, but in the second round, it will n over 2, and n over 4, and n over 8. And if you sum this together, it will just simply be n. So the prover can easily do it in the linear time. And this is all known as the result for the multivariate sum check and the prior inner product argument. But the problem is how to do this in a streaming way.
Can you hear us?
Yeah.
Yes.
I have a question.
Oh, I didn't hear you. Sorry.
Yeah. Could you go back to the inner product?
Sorry.
Oh yeah. So my question is that I just want to make sure it's the purpose of folding is the trade-off between time and space. So before folding,
I think depends. Actually, this it's hard to say it's a trade-off between time and space, because it's also this folding is also benefits. We can also get benefit from this folding for the time, because verify two vector with size n whether the inner product is equal to a claimed result is very hard for the verifier. And but if you can reduce this problem to a smaller problem, which means that you do a divide and counter, and then finally this problem will be reduced to a constant size problem, and this can be done by the verifier efficiently. And actually this result is this folding technique is also commonly used in the other time efficient protocol like multivariate sum check or the scalar product or grand product protocol. They all need this kind of reduction, this folding reduction process. So I think it's not just for the space and the time trade-off. It's also the way how we solve this kind of proving problem, how to generate, how to build an efficient proving system. This kind of techniques is really useful. And actually, there are also some, other technique like the sum check, univariate sum check used in Martin and Aurora. They do not have this reduction, but instead they only have one round of computation. I think that is kind of time and space trade-off, because their time is is quasi-linear. So this inner product argument is linear time, but the sum check used in Martin and Aurora is quasi-linear, is n log n time. But the benefit for them is that they only have one round protocol, so the proof size is constant. In contrast here, the proof size is actually log n. So in this sense, it's kind of like a trade-off between the proving time and the proof size. So it's still a trade-off between the time and the space, but it's not about the prover time and the prover space. It's about the prover time and the proof space, like that. Yeah, thanks for your question.
Yeah, thank you.
Yeah, so as you can see here, we are actually incurs a lot of communication costs. We have log n round, so the proof size is increased by log n. But the benefit is that we can have a linear time proving algorithm. In contrast, if you do not have this folding, you have only one round, then the proof size is very short, but the proving time may increase. Yeah, that's my point.
I see.
Okay, so now I want to talk about how to stream the prover's message. It's about how to generate the prover's message in a streaming way. So the thing is that we can view the element of the vector f. I mean, now we have the streaming access of this vector f. So each time you have one f0, f1, f2, f3, you can fetch it from this string. And also we have the stack, and the prover then will maintain a stack, and each time it will fetch an element from this string f. And whenever they fetch two elements, they find that they are in the same level, then that means that suppose we are doing the even and odd folding. If they fetch two elements at the same level, then that means that it can do the folding for these two elements, and it will get an element for the next level. So f0 prime is the first element of the next level. And also so on. It will and so it will fetch the f2, but f0 prime and f2 is not on the same round, it's in different level. Then it will fetch f3, and they will find that f2 and f3 can be merged together, can be folding using the randomness. Then they will get f1 prime, and then you will find that f0 prime and f1 prime are on the same round. Then you can fold these two together, and then finally you will get the first element of the third round, which is f0 prime prime. And in this way, we can just maintain a stack and process the element in the string one by one. And you can see that the size of the stack is at most log n, because whenever you fetch two elements at the same round, then you will merge together. So it will always store the stack will always store the element from the different round. So and they are only log n round. So the size of the stack is also log n. And the whole computation can be viewed as a tree structure like that. And the overall proving algorithm can use the log n space to generate the vector for any round. But the thing is that you cannot store the any vectors besides the stack. You cannot except the stack. You cannot store any intermediate a whole vector into memory. So at each round, so you have log n round. At each round, you need to spend the linear time to compute the elements for this round. So the overall, if there are n log n rounds, then the overall computation complexity will be n log n. And there's some cool thing here is that we can actually exploit the divide and conquer structure. We can exploit this recursive structure, and we will find that at some level, the whole vector for this round is able to be stored into the memory. So you can set a threshold level or threshold memory budget, and when you find that the vector size in this round is already can be fed into the memory itself, then start from this round, you can just use the time efficient protocol to process the rest of the proof generation. So when you do the large proving instance, like outside the threshold, you use the space efficient realization. Just use the stack and fetch the element and create the stream of the vector for each round. And at some point, we will find that the vector itself can be stored in the memory. Then you just create the whole vector in this level, and then continue with the time efficient realization for the rest of the protocol. And the overall complexity is that for the arbitrary size is n log n, and when you below the threshold for the memory budget, it's only require linear time. Yeah, this is how we realize the elastic in the product. Question on this? Okay, then I'll continue. So previously, as I said, at the end of inner product, we require the verifier need to verify a multivariate polynomial evaluation of the f, because in the final round, the proof of set FNGN, which can be viewed as a linear combination of the R1, R2, or the randomness with the element in F. So so we can really instantiate this with a multivariate polynomial commitment. So in the ideal world, we will have this polynomial IOP, polynomial interactive Euler proof, which has the multivariate polynomial query. But in real, we can instantiate this with a multivariate polynomial commitment scheme. So the thing is that the verifier can just commit the element in F using the multivariate polynomial commitment scheme. And finally, the verifier just fetch the multivariate polynomial evaluation from the polynomial commitment scheme. But in Gemini, we do it in a different way. Is that we use a Tensorcheck to reduce this multivariate polynomial query into a univariate polynomial query, so that instead of using the multivariate polynomial commitment scheme, we can just use the univariate polynomial commitment scheme. For example, we can just use KZG or other univariate technique here. And there are several benefits of this design. So first, the KZG, we found that it's very stream friendly. I mean, as I will show later, it's really stream friendly. So we really don't need to care much about how to stream the KZG. And the second is that we found that by using this Tensorcheck and some latest batching technique in the KZG, we can actually reduce the verification cost. So if we use the multivariate polynomial commitment scheme directly, then it will incur a log n evaluation proof. The evaluation proof will contain log n group element. And the second, the verifier in the multivariate polynomial commitment scheme will require log n pairing. But by using our Tensorcheck and the univariate technique, we will find that the verifier only needs constant pairing. So namely just 2 pairing. And also the evaluation proof size is just constant by using the batching technique. Yeah. And now I want to briefly share some thoughts about how to achieve this Tensorcheck. So, or how to reduce this multivariate polynomial query to a univariate query is that we find a mapping between the multivariate polynomial and the univariate polynomial. So here are 2 polynomial. One is F, the first one is multivariate, and the second one is univariate. And both of them have the identical coefficient. So AZ, A1, A2. And we found that this coefficient will have some, they are in some identical location. So for example, if you just fix the first variable of the multivariate polynomial to be an evaluation point like R1, then you will find that this actually means that you fold the univariate polynomial by using this R1. So you fold the even and odd part using this R1. And so we find this mapping between the multivariate and univariate. And the evaluation basically means that you fold this univariate polynomial n times, and each time you use one randomness like R1, R2, and 2Rn. And that's the reason why we say that the final result of the inner product is a multivariate evaluation. But on the other hand, that also means that if we do not use the multivariate polynomial evaluation to evaluate it, we can just verify the relation of this folding. So each time we check whether the folding in this round match the result from the last round, then we can still get this result. And this is the basic idea of Tensorcheck. So sorry, does anyone have a question? Okay.
Sorry, I'm still a little confused. Like, what is the Tensorcheck trying to check?
The Tensorcheck is that so normally, as I said, we need to query the polynomial f using the multivariate polynomial commitment scheme. And the purpose is that we do not want to use the multivariate polynomial commitment scheme because it's inefficient. We want to use the univariate polynomial polynomial commitment. How do we do that? And the way we do that is Tensorcheck. It's a method to reduce the multivariate evaluation to a univariate evaluation. So my point is that instead of evaluate the multivariate polynomial f at point R1, R2, and Rn, instead of doing that, we can doing the tensor check of the folding relation. We check that F1 and F2 are folding correctly, F2 and F3 are folding correctly, and F2 are Fn. And this can also give us the desired result. And in this process, we are working with univariate polynomial only, and I have no multivariate polynomial. So this is a tensor check. So it's actually a method to avoid the multivariate polynomial evaluation.
Do you want to avoid multivariate because it has a logarithmic overhead? Is that the reason why?
Yeah, we found that with the tensor check and the batching technique from the KZG, it's actually more efficient than the multivariate polynomial commitment.
Okay.
Yeah. Yeah. So this is the inner product protocol, as I showed before. And how the tensor check looks like is that in the later round, the prover will just send all the intermediate folding result to the verifier. And the verifier will just send the evaluation point beta back to the prover. And the verifier will the prover will send the evaluation results, and the verifier will check each round the fi is folding correctly using the polynomial in the fi-1 round. And actually this idea is also used in the low degree testing in the Fry protocol. You will find that you only need to query the univariate polynomial at the point beta square, beta, and minus beta. Then by the Schwarz-Zippel lemma, you will find that if this equation holds, then the folding relation will also hold. And this is essentially the tensor check. Yeah, and actually this also means another way to view this tensor check is that it potentially means that we have a more efficient multivariate polynomial commitment. We can construct a more efficient multivariate polynomial commitment by using the technique in the KZG, in the batching KZG, and also our tensor check. It's possible to combine these two techniques to create a more efficient multivariate polynomial commitment. And actually, there are several people send an email to me and actually ask about this direction, and I think they are working on this. Yeah. So in other words, our tensor check also shows the possibility of constructing a more efficient multivariate polynomial commitment. Yeah.
Question.
Yeah, any question?
So maybe this is exactly what you said, but I just wanted to confirm. Are you saying that using tensor checks, there is a generic way to build a multivariate polynomial commitment scheme just given a univariate polynomial commitment scheme?
That's what we do in Gemini. So what we do in Gemini is to use the tensor check and the batching technique in the KZG to achieve this multivariate evaluation. What I said is that by extract the idea from this tensor check and the idea from the batching KZG, it's possible to build a standalone multivariate polynomial commitment scheme that is more efficient than existing one, than the existing PST multivariate polynomial commitment scheme. That's my point. Yeah.
So just to clarify, your techniques crucially rely on the structure of the KZG commitment scheme. Is that correct?
Crucially relies on the batching technique of the KZG. So recently there is a paper, I think it's BCGH. I don't remember. It's a Bonnet's paper. They prove that using the KZG, you can batch the evaluation result, evaluation opening proof. So if you want to evaluate a single polynomial to multiple different evaluation points, it proves that you can just use one single group element and use just constant pairing, just use two pairing. The verifier only needs two pairing to do so. This is a recent batching technique used in the KZG, and we leverage it here. Yeah. Because as you can see here, we need to evaluate this univariate polynomial at 3 different points, the beta square, beta, and minus beta. But by using the batching technique from the KZG, all this, even if you need to evaluate at 3 different points, you only need one single evaluation proof and one single group element.
Thanks.
Okay. Thank you. Yeah, yeah. Finally, I want to briefly talk about the KZG, how to stream KZG. Although it's very easy because KZG is really streaming friendly. Just some very simple reminder. So the KZG, the committer key is just a power of tau. It's just several group elements. And if you want to commit a polynomial, you just do the multiscalar multiplication between the coefficient of this polynomial and the committer key. And how to do this in a streaming way is also very easy. You have the stream of this stream of the coefficient of this polynomial, and also you have the stream of this committer key. So how to commit is very easy. Is that you just do the multiplication and aggregate and multiplication and aggregate. So it's very easy to compute the commitment because it's the multiscalar multiplication itself is also already stream friendly. And the thing is that how to do the evaluation. So in the evaluation, we need to commit to the quotient polynomial of f. So we will divide the polynomial f with the polynomial x minus alpha, where alpha is the evaluation point, and you will commit to the quotient polynomial q, and this is the evaluation proof. So we already know how to do the commit very efficiently in streaming way. The thing is that how to do the division, but as you can see, the division here is also very simple because you are actually divide the polynomial x minus alpha, which has only 2 coefficients. So you just apply the Riffen's law of recursivity and do a pen and pencil division, and you can easily find the coefficient of the quotient polynomial q, and then you just need to commit to this polynomial, and then you can get the evaluation proof in a streaming way. Yeah, that's another reason why we like the streaming KZG. Why we like KZG, because it's streaming friendly. And finally, as I said, in the KZG, there are some recent papers show that there are some very nice batching technique. And this is some brief idea. So suppose you want to evaluate the univariate polynomial f at m different evaluation point. So you want to evaluate at alpha 1, alpha 2, up to alpha m. How to do the evaluation proof, how to do the batching evaluation proof. The idea is also very simple. You just divide by a polynomial x minus alpha. So this Vx is a vanishing polynomial over this evaluation point. We just divide this polynomial f with this vanishing polynomial v and get the quotient polynomial q, and just commit to this quotient polynomial. And this is a batch evaluation proof. And as you can see, it's just commit to a single quotient polynomial, so only a single group element is needed, and also the verification also only needs 2 pairing, which is also very good. Yeah, so this is how the KZG do the batching. Yeah, any question on the polynomial commitments part? Okay, so finally, I just give an overview of the Gemini stack. So at the bottom, we have the polynomial commitment scheme. So it can be either univariate using the KZG and Tensorcheck, or multivariate like PST. And the middle, we build an elastic inner product. And actually, with these components, we already is able to build a non-preprocessing succinct argument. But if we want to build succinct pre-processing succinct argument, we are actually requires some more work. We need to prove some lookup relation, and also we need to elaborate a grand product protocol. And it's more, and actually it's very tricky because some lookup protocol is not compatible with the string algorithm. But I don't have time to talk about them today. Please refer to our paper for the detail. And today I just talk about some basic building block like in the product and the Tensorcheck and the elastic KZG. And finally, I want to talk about some of our implementation and the benchmark results. So implement this Gemini is actually not an easy task because we need to implement all of this protocol in 2 different modes. We will have one time efficient implementation and also have a space efficient implementation. So it's like a twice work, twice than the normal work we need for the other paper. So it takes us about 1 year to finish the whole implementation. And also we find that some of our implementation is already open source in our arkworks library. And also we upload some of our module to the arkworks library, like our streaming KZG. We put it in the arkworks polynomial commitment library. And we hope some later work which builds on top of arkworks can benefit from it. And also we realize our stream using the Rust feature, using the Rust iterator. And because Rust is a type safe system, it's actually also a very annoying task because we must embed the computation tree in this tab. We must specify how this stream is composed. And actually this is a very heavy task due to the restriction of the Rust. But also this is a price of the efficient implementation. And finally, I want to show some benchmark result. So many prior work like Marlin, Spartan, Planck, they all stop at the millions of gates, like 2 to the million, 2 to the 20. But in Gemini, we are actually really support hundreds of billions of gates. So we can even support 2 to the 77. I mean, that's large instance. And actually, we found that even if we use the time efficient implementation only, and even if we run it on a very powerful AWS machine, like it have 70 gigabyte memory, it still will stop at 2 to the 27. So all the later results, we really need our streaming technique to run it. And also we do the benchmark our pre-processing, and it will even stop earlier, like 2 to the 25, because the proof algorithm becomes even more heavy. And the things to note here is that, well, as I said, our proving time is n log square n, but the log factor does not show up here. And the main reason is that the cost, the proving time cost, is dominated by the multi-scalar multiplication. So the log factor will not kick in here. And this is our proving space. Although I said the prover only need the log space, but again, I also said we can set a memory budget, and which allows the prover to switch from space efficient to the time efficient. So here we just set 1 gigabyte, and once the statement can be loaded into the 1 gigabyte memory, then we will switch back to the time efficient implementation automatically. And as you can see here, there will be a flight line if the instance size is greater than 1 gigabyte. So much for this. Here are some resources of our paper and our code. And I'd like to hear your comments and questions. Thank you. Yeah, any question?
So I had a question. Great that you guys can go beyond 2 to 20, which I think has been a concern for a long time. But I still think you guys stop at 2 to the 37 or something. What do you think we need to go beyond?
you mean beyond the 2 to the 37?
Yeah, yeah.
I think there's nothing stop us from going beyond. I mean, there's nothing on the space part stopping us from doing so. The main bottleneck is still about the time. So as I said, our time is n log square n. And when the only thing stop us from doing so is that right now it takes us about 2 weeks, for example, 2 weeks to generate the proof for the size of 2 to the 37. But if you go beyond 2 to the 37, it will also beyond the 2 weeks. For example, it may take several years for you to doing so. I think it's unacceptable. So on the space part, on the memory part, I think there's nothing limited us. The only thing limited is that it may take too long time for us to generate the proof for even bigger instance. Yeah. Thank you for your question.
Maybe another one. So what are these instances that have these many constraints? What are these instances? Are you doing like Merkle or are you doing SHA? What are you doing? What are you?
Yeah. Right now we are doing some dummy instance. So we just create a small matrix which has some specific pattern, and we just repeat it several times. And this allows us to generate the dummy string very efficiently. So this allows us to benchmark it on it very easily. And I think that's an interesting question. Can we really create a real big and useful constraint? So it's not a dummy constraint, it's really a useful constraint, and which has a very large instance size. And can we do the proving of it? We didn't do that in our paper. We just use some dummy constraint, which allow us to do the benchmark efficiently.
Thanks.
Thank you.
Yeah, I also have a couple of questions. Do you want to go back to the slide where the prover is getting the trace of the computation string to it?
Yeah, this one. Yeah.
So I assume in practice, like some machine would have to compute AZ, right? Which could be expensive and could be like losing all the space efficiency. But you said that there's certain types of computations where that's not the case. Can you go a little bit more into this?
Yeah, the thing is that when you compute the AZ, if the matrix A is fully it's kind of a random matrix, then you really need a random access to the Z itself. You need to skip from one element to another and so on to compute the AZ. But if the matrix have some kind of nice property, for example, the non-zero entry have some pattern, so that you can predict how it will use the element in that. In this way, you can generate this computation trace very easily. Yeah, but actually in our paper we didn't talk about how to generate this computation trace. We think it's as outside the scope of our paper. We just assume the prover has the computation trace and has the circuit intermediate result. Yeah.
Okay.
Yeah, but this is really a good point. If you cannot compute this computation trace efficiently, then there's no sense for generated proof efficiently. Thank you.
Any other questions? If not, then we can thank.
Yeah. So if you have any questions, so feel free to send me the email, or we can schedule an online call. Yeah. Thank you for the invitation. I'm very happy to share our work here. Yeah.
Thank you. Thank you so much.